Hi all, this is Vishwanath Verma in the Korea and I am here to do my presentation for. So the first paper is on learning real-time A-star path planner for unmanned air vehicle, which is target sensing. So about the paper, uh, a way organized for identifying closely spaced targets from a fixed wing unmanned area vehicles with a characterized sensing impression is displayed in this paper. So the organizer employs the learning real-time A-star and look into the calculations to supply powerfully doable ways to achieve the detecting objectives within the most reduced sum of time. So by consecutively building primitive turn and straight segments of a specific step measure from the UAV's beginning position, a tree of conceivable paths that span the range of integrated is delivered. An LRTA star uh, look on look of the tree returns attainable ways at any point amid execution and least length ways of on the off chains that connected all the way through. So the running time and the path length execution of the search are straightforwardly affected by the working parameters of the LRTA star algorithm. So to progress the running time of the organizer, uh, altered LRTA star search that ends when there is no advancement within the way for a predefined number of iterations is actualized. So the result could be a way planner that produces short distance ways in acceptably brief running times. So next comes the introduction. So the way of arranging is a basic action for portable independent vehicles. So autonomous fixed wing or flying machine, the path planning issue is especially troublesome since the dynamic limitations of the flying machine, such as least turning span, must be considered amid the path planning handle. So airborne detecting of ground ground-based targets includes uh, or encourages trouble to the problem by requiring the impression of a downward looking sensor to pass over a gather of targets. So the path planning handle must uh, not as it were consider the air ship elements, but also the development of the sensor impression as the airplane takes after an indicated way. So in case the targets are found distant, separated with regard to the least turning span of the vehicle, at that point, the path planning approach is direct. So next comes the issue in the work. So the issue of this work is to create a path planning strategy for sensing a gather of closely spaced targets that completely utilizes the arranging adaptability given by the sensor impression, whereas working inside the energetic limitations of the flying machine. So the path planning objective is to play down the wavelength required to see all the targets. So this problem is outlined in figure 1 here, where there are three targets. In intending to issues of this nature, three specialized challenges uh, must be tended to: coupling between way segments, utilization of sensor impression, and assurance of the seeing a range of the targets. So the approaches to the problem. Uh, a standard approach for arranging ways is to arrange way selections that are ideal for one pointer to another. So for different targets, the approach includes arranging an ideal path from the beginning point to the primary target and from the primary target to the movement target and so on until all targets are gone to. In case targets are broadly divided relative to turning capabilities of the vehicle, at that point, this approach works well, given that the ideal visit range can be specified. On the off chance the targets are closely dispersed, at that point, coupling between the way sections due to the energetic confinements of the vehicle can result in a distributive result for the composite way. So next is the discrete step paths. So, effective path planning calculation ought to create a sort of way that's not uh, constrained by focuses or headings, that utilizes the complete capability of the vehicle sensors, and that fulfills the energetic impressions of the vehicle. So these capabilities can be provided by discrete step ways, which are built by collecting primitive turn and stride segments to frame a flyable way. So for this work, each primitive portion is a discrete step way, uh, is of an indicated length ds, and is either a turn made at the least turning span of the vehicle or a straight line. So it is naturally clear that the shorter step lengths increment the determination of the way tree, which more profound trees permit paths of more noteworthy length, uh, expanding the scope of region of the tree. So given that number of nodes noteworthy length, expanding the scope region of the tree. So the given that the number of nodes in a tree develops exponentially with the profundity of the tree, there are down to earth restrictions to tree profoundly forced by computer memory limits. And LRTA start research. So this work applies to the learning real-time A star calculations in a novel way to learn which department of characterized way tree best fulfills the specified way arranging objectives. So the LRTA star calculations is well built up and has ordinarily been connected to path planning problems in a lattice-based universe. So in common, the LRTA calculations may be connected to any type of world, network tree, coordinated chart, or other. The LRTA star calculation is chosen over the fastest A star calculation since the restricting figure on the execution of the path planner is memory spaced while required to store the extended hubs. So by utilizing LRTA star, execution speeds is yielded to decrease the spatial complexity of the loop. And next, the algorithm details. So the LRTA star calculation itself is basic and rich. Each hub encompasses a heuristic estimation h of the remaining subnet that must be traveled to a total of unfinished objectives. So at each step of the loop, the current hub calculates FC, where HC is the child of the heuristic uprise and KC is fetched of moving to the particular child. In other words, FC is evaluated remaining traveled remove in the event that a move were to be made to child C. The current hub upgrades its heuristic value H, and after that moves to the comparing child. So at this point, the look has learned the minimum length way that finishes the desired objectives. So it is attained to move back uh, up to the tree to a node's parent and proceed the loop from there and within the conventional A star loop. By doing so, also comes about in expansive parcels of the tree being explored without finding distance better, a much better or higher, a stronger and improved, and a very better way. And next is initial heuristic. So the essential necessary of the LRTA star log is that hello there, which is h into I, is continuously genuine for any node I. So the reason for the necessity is basic. In case a hub on the ideal way overestimates the remove to the objective, uh, the loop may never move that hub and consequently never find the ideal way. Heuristic that constantly appraises the genuine wavelength are termed admissible heuristics, and the calculation of suitable starting values of these heuristics is basic, and the execution of the LRTL loop. So it would be allowed to initialize the heuristic to 0, but that would require a long time to memorize the ideal path. So heuristic within the LRTA star tree search issue are causes of the remove that must be traveled from the current hub to complete the remaining errands and terminating conditions. So the strategy utilized to end the tree look specifically influences the speed and path length performance of the tree look. On one extraordinary, uh, the look runs until the heuristic alter is zero. In this way, ensuring that the minimum length way has been found, but conceivably require a critical sum of running time. On the other hand, extraordinary, the look runs until a maximum running time is come to, hence ensuring n by a certain time, but with the resulting way conceivably uh, being distance from ideal. So not one or other of these extremes is exceptionally alluring for the path planning issue and the branch terminals. So memory administration and pruning of the weight tree are basic to get great execution of the LRTA star tree look. When the currently explored department gets to be longer than the present best way, the current hub is ended by erasing its child and setting its heuristic value to intermediateably, and the look is restarted at the root hub. So in the event that a node's child has all the heuristic values of boundlessness, at that point the hub could be a dead end and it could be ended similarly. Also, since the heuristic estimate of a hub is continuously less than or break even with to the real wavelength, the heuristic can be utilized to winnow hubs from the tree and path size trees. So a noteworthy issue with looking the way tree is the estimate of the tree. So as the step size decreases, the measure of the tree increments exceptionally rapidly, which makes investigating the tree a lengthy process. So the total weight tree includes a measure of 3D where T is the number of levels within the tree. So this means that for a tree with 30 levels, there are roughly 3.1 cross 1014 hubs. Although the look will not have to be investigate all the hubs, there will be a huge number that must be evaluated, meaning the look will be moderate and require a part of memory space to store the visited hubs. And next comes the step size selection. So the LRTA start relook will continuously find the most brief way for a discrete step weight tree. So in hypothesis, the real worldwide ideal may be found by lessening the step estimate within the LRTA start tree, look to an impeccably little value. So the key to effective LRTA tree look is to choose a step estimate that's little sufficient to best inexact the worldwide ideal, whereas not making the tree as well endless to look quickly. And next is testing and comparison. So a set of uh, 2000 targets, a target circumstances delivered for a 2 RT by 2 RT world was utilized uh, to assess the LRTA and NILRTA star calculation. So each situation has three targets chosen at irregular as well as starting positions and heading for the vehicle that was chosen at random. So the calculations were constrained to one dimension of execution time, and information of early terminated ways was utilized within the analysis, and it can be seen that the raising the step measure decreases the algorithm's running time, whereas phase somewhat expanding the of length of the resultant path. So LRTA tree search validation. So to illustrate the preference of the LRTA tree look, a comparison was made between the way created by the LRTA calculation and by the way found through a brute force global search based on the Dubin's way. So the measure of the sensor impression for the LRTA calculation was reduced to summarize the vehicle passing through the largest forces. So figure A shows the LRTA star tree look produces roughly the same minimum length value as the brute force worldwide look, with the LRTA way being as it was 0.5% longer. So next is the path length. So the path length execution. Uh, so this thing is a cruel wavelength increments which around 19% over the range of step sizes, demonstrating the little step sizes are superior. So the increments within the cruel path length between are zero point 0.2 and zero point 0.4 radians. Uh, be that as it may, it was 6.8%, which illustrates the decreasing utility of utilizing little step sizes. So the path length execution for the two calculations at different step sizes is present in the figure. Next, the running times. So as in the above figure, the LRTA and NILRTA star algorithms running times with the normal generally running times for both strategies at different step sizes, which is plotted in A. The LRTA star strategy takes around 8, 80,000 hubs 10 seconds to run at D, which is a value of zero point 0.2 radians, whereas the NILRTA star calculation takes almost 150,000 hubs. So the LRTA star algorithm's cruel running time brings down the generally 2 lakh hubs with a step measure of zero point 0.3 radians, a 98% decrease. And next comes different types of targets. So this comes about displayed hence distance for all assembled utilizing scenarios with 3 targets. So to test the algorithm's execution for diverse number of targets, 2000 irregular target scenarios are utilized for each number of targets between 1 and 8 with a step measure of tests of 0.25 radians. So for 8 targets, the LRT star algorithm visits an normal 5.5 million hubs compared to the NILRTA star algorithm, which visits an normal 2 lakh hubs. So on the conclusion, so the LRTA star and NILRTA tree search calculations are displayed in this paper, which finds the department from the discrete step way tree that best accomplishes a set of indicated targets. So the LRTA calculation will continuously create the most brief way, but uh, it will take longer to run. And the NILRTA star calculation succeeds in relinquishing a few path length execution in trade for significantly quicker running times. So by maintaining a strategic distance from the impacts of coupling between waste sections, the LRTA star and NILRTA star calculations arrange ideal or near optimal ways by means of various objectives. And this is the second paper, the simple subgoaling for real-time search. So the abstract. So the real-time heuristic look calculations fulfill a constant bound of on the sum of arranging per activity autonomous of public estimate. So as a result, they scale up well as issue become bigger. So this property would make them well suited for video diversification diversions while where manufactured insights control agents must respond rapidly to client commands and to the other agent actions. So on the drawbacks, real-time look calculations employ learning strategies that regularly lead to distributive arrangement quality and cause the specialist to seem silly by re- uh, returning to the same problem states over and over. So introduction. So this is a typical issue in computer games is looking for a way between two areas. So fake insights control specialists in video games must respond rapidly to players' commands, and other agents. So a common issue in video recreations is looking for way between two areas. So in this setting, the real-time limitation extremely limits the extent of applicable heuristic look calculations. So as a result, arrangement quality can be very low and outwardly the shoring conduct is seen as silly. The sub-goal database construction. So our inspiration is to hold the LRTA star amazing performance while streamlining the calculations and unwinding memory requirements. So the foremost memory consuming portion of DLRTA lies with its sub-goal database. So to build the database, so the DLRTS to begin with abstracts the outline using the click reflection conspire of PRA star. So figure here outlines the method. So a grid based outline A is changed over to the chart B, which is at that point preoccupied so that every click of unique states get to be single unique state C. So once the deliberation is total, a ground level state closest to the centroid of the click is chosen as a representative for a unique state. So the agents are checked with little white circles in portion D, and ground level states abstracting to distinctive theoretical states as shown as districts of distinctive shades. So sub-goal database construction. So after this separating of the direct into districts, the DLRTA star considers approximately all sets of conceptual states. So for every match they make, it finds a perfect way between the ground level operation and the two hypothetical states, which put it in a good manner. So at this point of time, they after takes after the wave from starting agent and marks the ground level state where the way enters the taking after zone. The self-evident state is put absent as the sub-goal for the match of the hypothetical states. So the memory necessities are O into V plus V2 dash, where V is the number of ground level states and V star is the amount of hypothetical states at consideration. So the sub-goal database construction. So we set off to think of a lesser complex approach to building a sub-goal database here. Uh, so the foremost clear and fastest step of continuous look calculations is LRTA star with a look ahead of one. Such a particularly blind LRTA star is really fundamental incline climbing increased with Bellman overhaul run the show for the heuristic. To go without from learning and the issue is causes, we would like a LRTA star not to memorize more frequently than before. So this can be finished by choosing a sub goal which is satisfactory near the master to be reachable through direct incline climbing. So the runtime search. So when the master finds out the information set record for the most part comparable to its show circumstance, it sets the sub goals S dash sub goals from the record similar to claim sub goal and proceeds towards it utilizing the standard LRTA star. So there are many issues to address. To begin with, the around the world objective can be slant climbing reachable from the specialist display status, but at that point, the master might select a sub goal driving it absent from the objective. So we address this by checking on the off chance that the around the world objective is inclined climbing reachable from the specialist display status. On the off chance, uh, this is away at a point, we had the worldwide objective and sphere of the sub goal insurance completely. So next, the imperial evaluation. usually addressed in a number of ways. To begin with, instead of essential hill climbing, we apply the LRTA star, so which guarantees that the sub goal will be come to at a few points. So to relieve the negative impacts of the learning handle, we use LRTA star with a more profound look ahead D, which has been appeared to decrease learning. So secondly, able to proactivate by raising the database's record check in an endeavor to extend the uh, similitude between the age and circumstance and the database's closest coordinating record. So performance metrics. So the DLRTA star within the cleared out subplot, within the right subplot, both drop exterior, the run uh, delineated with the charts. So it grows over 42 states per move. So table one contains the table in the picture, uh, provides information for all parameters of the LRTA star and the KNN LRTA star, as well as the fundamental LRTA star. So the sub-goal database pre-completions time, measure, arrangements, suboptimality, and number of states extended each move and the columns. To summarize, we can state that the KNN LRTA star performs slightly worse than the D LRTA star while requiring considerably less memory for its sub-goal databases. So the trade-off is attractive for pathfinding in video games, especially on the consoles where memory is often a scarce resource. So the benefit comes at an expense of somewhat longer computation times for generating the sub-goal database for a more complex runtime. So coming to the conclusion, the essential drive behind this work was to create a high performance real-time look calculation reasonable for pathfinding in video diversifications by winding memory requirements of the LRTA current state of the art real-time search applications. So the modern calculations KNN star, LRTA star offers clear benefits for pathfinding applications in video games. So as a future work, the authors accept that the KNN and LRTA star can be further improved to completely coordinate the LRTA star runtime performance. So this is how the authors organized a few roads for potential improvements. Thank you. And that's all about my presentation.